This is one of several scenario comparisons between a swept spectrum analyzer such as the Agilent E4440A or PSA and the Tektronix RSA5100A with DPX. Starting with the PSA, we'll use a scenario of an unknown problem with a device under test. We know there's a problem with the device, but we have no idea what the problem is or what it looks like. Now let's look at how to go about troubleshooting that problem. The center frequency in this case is 2.4453 GHz, and the span is set for 10 MHz. There's not much to see when we monitor this signal. There's a relatively steady frequency, but nothing else that we would find helpful. So we've turned on a max hold trace to see if we can get any more information about the signal. Using the default settings of the instrument and a max hold trace, there's a resolution bandwidth of 91 kHz, a span of 10 MHz, and a sweep time of 1.12 milliseconds. There's still very little helpful information being acquired. Again, we know there's a problem, we want to know more about it, and the task is to see if we can capture and identify it. We'll let this run for a while to see if anything does show up. This is what the max hold trace looks like after running for 10 minutes. All this really tells us is that there's some sort of glitching occurring, but it's difficult to say for certain what it is. There does appear to be either some frequency drift in the signal itself, or other signals could be appearing in this spectrum as well. It's just too difficult to say based on the limited information that the Agilent PSA provides. So now we'll do a max hold again, but this time we'll try slowing down the sweep time. The premise now being that if something is happening very quickly and we dwell at each specific point longer, there's a higher probability of seeing a quickly moving, infrequently occurring event. However, the drawback is that we're also missing more information by staying longer at any one specific frequency. So the limitation with this approach is that we get no idea how often the transient appears at any one point. We only know that it was at each of the points once. So with the sweep time changed to 1 second, we should start to see hits on the max hold trace more frequently. Now, to increase our confidence that we'll capture some information about the transient event, we'll slow down the sweep time even more, to 1 minute now. So, after about 5 sweeps at this rate, we might be able to conclude that this is not just a spuriously occurring signal, but that our main signal is wandering around. From these results, we know which frequencies it's going to, but we know nothing about how often it goes to each frequency and how long it stays at any one particular frequency. With a sweep time that was slow enough, and particularly with a signal that happened to have occurred often enough that it could be captured, the Agilent PSA gave us a partial analysis. And how long did it take to get it? 15 minutes, with about 10 minutes using the fast sweep to figure out there was a problem, and another 5 minutes using the 1 minute sweep time trying to get some more information. Here we see the exact same signal on the RSA5100A. Along with adjusting the settings so that they're comparable to the PSA, we'll also do some other things that will help discover the transient disruption of the signal. Using what's called digital phosphor technology, or DPX, we'll start with a max hold trace. We'll also set up something new on the DPX signal called temperature processing with infinite persistence. DPX has dedicated hardware that can process 48,000 spectrum measurements per second. That means it's taking a fast enough sample rate and performing a discrete Fourier transform quickly enough to achieve this analysis rate. The DPX display shows you what it sees in a usable form for the human eye by updating a persistence display 20 to 30 times a second. A persistence display means that every pixel or frequency and power value has an associated persistence or intensity value. There is a histogram of data associated with each pixel, and this drives the intensity or color of each pixel. Because we're referring to temperature processing, events that happen more frequently get a higher intensity or hotter color assigned to them. This way we get a much better sense of the time-varying behavior of signals. By capturing and displaying the signal like this, we can very quickly see a similar envelope for this particular signal, which took several minutes to show with the Agilent PSA. DPX allows you to see frequency events occurring in as short a period of time as 24 microseconds. Here we're not only able to see the envelope of this transient signal, but we can also see some specific frequencies at which it appears to be settling, with a transition where it overshoots the frequencies and settles on the new frequency. We can see the main carrier frequency, plus another frequency where the signal jumps, and we also get a waveform buildup showing the actual transition between the two frequencies. With DPX, we can quickly and easily see that the signal is hopping at some stage from its main frequency to the higher frequency and then back again, staying at the main frequency for longer periods of time. We're also seeing overshoot, so we suspect the problem is because our phase lock loop is temporarily losing lock and changing the output frequency. Finally, because of the persistence display, we can see that the problem is repeating and always hopping to the same frequency. The next thing we can do with the RSA5100A that we didn't have available to us with the PSA is the ability to trigger and capture that specific frequency transient event. After we observe the transient frequency event with the digital phosphor spectrum display, we can set up the RSA to use the frequency mask trigger, which can selectively trigger on changes in the frequency domain, capture the entire transient into memory, and analyze it. This greatly simplifies the troubleshooting process that would be required with a legacy spectrum analyzer. So, in switching over to spectrogram, which will show frequency changes over time, with time on the vertical, frequency on the horizontal, and color indicating power intensity, we can also increase our analysis length in the time overview window to 900 microseconds duration, anticipating that that might be a likely length of the transient event. Then, using the Tektronix patented frequency mask trigger, we can selectively trigger on that glitch. By altering the default mask tailored to our signal, we can cause a trigger every time the signal violates the area we've designated. The trigger captures 900 microseconds worth of information every time the signal moves from the main carrier frequency. Now we can see how the signal moves during the hop, and with markers and the zoom feature of spectrogram, we can completely characterize this repeating but hard-to-find hop. We can find out the settling time and how long it dwells at its other frequency before returning back. Also, in a time-correlated multi-domain view with frequency versus time, spectrogram, and a standard frequency domain display, placing and moving markers in one view will automatically correlate and update in the other views. So, if we want to see how a signal interacts at specific frequencies and times, the correlated markers provide a very quick way to assess that. If you're hunting for sources of interference in a design, DPX is an essential tool for finding elusive and hard-to-capture transient events, from glitches to signal interferences to changes lower down in a system design. With the power of DPX technology, you can isolate interferences and transient signals and very quickly characterize how they behave and what they look like.